All right, we're going to kind of stop where we were. We were talking about functions, asymptotes, continuity, how our functions behaving around asymptotes, horizontal, vertical asymptotes. We dealt with holes. We're kind of changing gears now, okay? Complete changing gears from the course from what we started with until right now, okay? So almost like a new day one. And we're starting with the slope of a line, stuff that we already know about, that we've already dealt with. Slopes of lines are huge in calculus, huge topic. And you're familiar with the change in y's over the change in x's. I want you to be familiar with the same formula, just using inputs and function values. So if I have an a, f of a, and a b, and f of b, we would produce the same formula for the slope of a line, f of b minus f of a over b minus a. It's the same thing, it's just function notation. Okay. We know if my line is going up from left to right, the slope is positive. The line is going down from left to right, we say the slope is negative. If it's horizontal, the slope is 0. If it's vertical, the slope is undefined. Okay. Well, let's also define the average rate of change of a function over an interval. We'll use AROC, A-R-O-C, short for average rate of change. Well, the average rate of change of a function is going to be the change in your function values over the change in your interval. Well, what's the change in function values? Well, you could say it's just the difference of two function values if your interval is from, say, a to b. This is the formula for the average rate of change of a function. It's the same exact formula for the slope. You will find in this class there are a lot of things that are going to mean a lot of things. You know, we'll have one guy that you're like, okay, I understand, but it's like, well, that also means a couple other things. So we have to be used to being able to apply multiple definitions for the same term, if that makes sense. Quickly, to show you graphically what average rate of change means, if you just draw a function and say you want to find the average rate of change of the function between this interval a and b, well, all you would need to do is find the point at a and the point at b, and if you connect the two with a line and you find the slope of that line, that is giving you the average rate of change of your function. This line is what we call a secant line. Now, you know the phrase secant from geometry. It's a line that passes through a circle just twice. Now, this line might pass through more than 2 times. However, if it's just passing through 2 distinct points that we're talking about, we'll say that's a secant line. When we say the slope of this secant line is the average rate of change of the function between a and b. What does average rate of change mean? Well, it's just telling you that on average, your function is doing this over this interval. So I look at this line and I find that the slope is negative. Let's say the slope is equal to negative like a half or something. Since I'm talking about some function f of x, I can say that on average between the x coordinates of a and b, my function values are decreasing. They're going down, 1.5 units per every 1 x unit. Now we can tell that it's not going to be consistently decreasing 1.5 units. We have certain situations where my function is increasing, it's kind of going up a little bit and go down quickly and then come up back a little bit, just saying on average that's what's happening. Okay, it's very important, and we're going to be talking a lot about just like changing things, like on average, how is something changing? And what's going to be applied a lot of times with changing things is things in the real world. And we can look at the change of real world things in this class, just like you do in like a physics class. So you will find that this class in physics will be really, really related. And we'll have lots of physics types questions in calculus class. Because physics is the math of change. Calculus is the math of change, and physics has a lot to do with change. So we're going to be dealing with position, velocity, and acceleration a lot in this class. So let's just remind ourselves about position, velocity, and acceleration. Position, typically, we will use the function x of t or s of t. Very important. Everybody, usually the first time they think about position, they get really confused. They think it's how far you've traveled. Position is just where you are located, not how far you have traveled. Okay? It's typically in meters. And we'll talk about more about, where you're located and what that could look like. The change in my position over a course of some time interval, we say is our displacement. Okay. Well, velocity, we've dealt with velocity before in physics. We say our velocity is our displacement over the time it took me to become displaced. Well, what is that? What is displacement? It's just the change in my position over the change in my time. Typically denoted by v of t. We would say v of t is equal to my change in my x of t's, which is my position, no, let me use the delta first, and then I'll move it down to the other. So the change in my x of t's, you don't have to erase anything. We'll just put it down over the change in time. How else can I write that? Well, guess how we're going to be able to write it. It's just the average rate of change, or the slope of my position. Velocity is simply average rate of change of my position, or my velocity can be considered the slope of position. Right, and if it's average rate of change of position, we'll talk about our average velocity, our velocity over a time interval. Okay, and then if we go a step further, this is typically in meters per second. You know, the change in my position, this will be in meters. The change in my time, that's seconds. Well, meters per second, that should make sense. Acceleration is going to be the change in your velocity over your change in time. And we can say, well, the change in my velocity is just the change in my velocity from, you know, one point to the other divided by my times right there. Times our x coordinates, v of b, v of a, y coordinates. What is that? That's just slope. So really, acceleration is just the average rate of change of velocity. Or acceleration is the slope of velocity. Average acceleration, average rate of change. Since velocity is in meters per second and time is still in seconds, what do you get? Meters per second squared. Meters divided by seconds times 1 over seconds equals meters per second squared. Typically, it's just A of t, which is what it's denoted. Okay, so this is really interesting, and this is a very key concept in this class. Very key concept in physics, though you might not have, you know, made the connection or really thought about it so much. The key concept is that, well, guess what? If you want to deal with velocity, you can just look at position and look at the slope of position to find velocity. If you're talking about acceleration, but you just have velocity, well, if you look at your slope of velocity, you'll have your acceleration. So slopes of one thing mean something else. Slopes of position give me a velocity. Slopes of velocity give me an acceleration. Okay? Now, we could be asked different questions to calculate the average rate of change. Let's just practice calculating the average rate of change. But you have calculated average rate of change before. It's a piece of cake. It's just slope. Okay? Here's a question. It says, we're given the following table of the position of an object, find the average rate of change of the object between 10 and 25 seconds. And what does your answer mean? Okay, so we just want to find the average rate of change. Now, before we go any further and calculate it, I want to make sure we understand what's going on with these values. So we have a position. Typically, position is done with a number line. Where you are located on a two-dimensional plane. And we could take an object, say a baseball, because it's easy to draw. Could that be a volleyball? No, I don't know how the volleyball things get patched together. Okay? Could be a basketball. Also is a basketball. No, it is a basketball. It's not a baseball. Sorry, the baseball doesn't have the line in the middle. You're right. I know. It could have been a tennis ball. Okay. Well, at time 0, being at position -2 does not mean I've moved -2, meters. I've moved 2 meters to the left. It just means that when I start my stopwatch, that basketball is located at position -2. Okay. Now, at time t equals 10 seconds, my position is at 6 meters. I don't know what happens between the 0th second and the 10th second. I don't know how this basketball travels to this position at 6 meters at the 10th second. This is very, very important. Okay? The table is just showing us snapshots. just pictures. It's taking a picture right at the 0 second, right at the 10th second, 15th second, 25th second, and in between those pictures, it is holding a hand up so you can't see what's going on. Does that make sense? Just like I don't know what's going on at 1 second, 2, 3, 4, 5, 6, 7, 8, 9, but then boom, I see it at 10 and I close it right away. And I see that the basketball is located at the 6 meter mark. This basketball could have gone all the way up to the 20th meter mark, came all the way back down, and then ended up at 6. It could have stayed at -2, hung out, and then at the 9th second quickly moved to 6. It could have done anything. This is the problem with looking at a table, is we don't know what's going on in between the timestamps, right? Now what we will say is that my displacement between 0 and 10 seconds was 8 meters, because the difference between those two, meter marks is a total of 8 meters, but I don't know my distance. I don't know how far I went to the right, how far I went to the left, whether I zigzagged like 20 times in the 10 seconds to get to meter mark 6. Does that make sense? Good, because like if I look at 6 and 10, doesn't mean my average velocity has been like 6 over 10. That has nothing to do with anything. That is just telling me I am located at the 6 meter mark at the 10th second. Okay? So keep that in your brains. Remember that. Now let's go back to the question, which is finding the average rate of change of the object between the 10th second and the 25th second. Well, at the 10th second, I'm located at the position 6. And then at the 25th second, I'm located at position 25. So snapshot here, and then at the snapshot of the 25th second, boom, I'm up there. We can find the average rate of change, which is just equal to the slope between the 2 points, which I can calculate. My two y values, or function values, subtracted from each other, divided by the coordinating x values subtracted from each other. Now, typically time is in seconds, and this is in meters. So meters up here, meters, seconds down here, meters divided by seconds. Okay, 19/15 meters per second. So we can say, okay, I don't know what happened between the 10th second and the 25th second, besides of the fact that the basketball was located at the 20th meter mark at the 15th second. But I know that on average, it traveled to the right at a rate of 19/15 meters per second, or 1 point whatever meters per second. I know it's easier to think about things in terms of decimals. We can say on average, the b-ball traveled to the right at a speed. The right denotes the positive or negative. If I'm moving to the right, velocity is positive. If I'm moving to the left, velocity is negative. Just to remind you that. Of 1.266 meters per second. That's just on average. Okay? That's a cool number. That just means you're moving to the right. You could have gone faster than that to the right. You could have gone to the left a little bit. We could have had positive velocity for a little bit of it, but then some negative velocity, but then back to positive. Okay? On average, that's what happens. Okay? We can do this. I could give you a function, ask you to find the average velocity given a position function. It's the same deal. But we're going to go back to the previous example in a second. So if I ask you to find the average velocity of the object given the interval, let's not use this interval. Let's use an interval of positive times, t equals 1 to t equals 4 seconds. Okay? All I need is 2 points to find the slope. Average velocity, it's important to connect all these things together. I'm trying to find my average velocity. Well, that's just going to be equal to the average rate of change of my position, which is just equal to the slope of my position function. All right, you guys calculate the average velocity of the object whose position is given by that function. So that means I can plug in any number that I want to into this function, and it'll tell me, where we are located. So that's interesting. I have the potential to have like a video camera rather than a camera that is just taking snapshots and won't let me see in between the snapshots. So very interesting. But it all comes down to really just slope. If the position was in meters and time was in seconds, it'd be on average going 2 meters per second to the right. Did I do my calculations correct? All right, cool. We can do that with another one. Okay. And what would that look like? Well, if I had a graph, if that was the graph and I graphed the thing right there, my average velocity would look like a line that connects 2 points, and the slope of the line would give me my average velocity. Okay, so if I have a graph of x of t, an infinite amount of collections, so from a function, if I connect 2 points, boom, I have the average velocity over that certain time frame. Okay, but let's go back to that same table. I think it's the same table. Maybe a couple of values are a little bit changed. Okay, and instead of a basketball, let's have a dude. And these are the positions of this dude over this time frame. It's just a table, so we're talking about a camera that just is taking a snapshot right at the 0th second, 5th, 10th, 15th, 20th second. Okay, and in between those seconds, we don't know what's happening. Okay? My question is, can I find the exact velocity of the object at the 10th second? Do I know exactly how quickly the dude is traveling and the direction the dude is traveling in at the 10th second looking at this table? We say yes. How?
Because for one of those points it gives you a position and time.
Okay. This is where we have our confusions. Okay, so if I'm trying to find my velocity at the 10th second, I'm located at the 20th meter mark. Does that mean I've traveled, or I'm traveling at that location 20 meters per 10 seconds or 2 meters per second?
No.
No, it doesn't, right? All I do know is that I traveled from the position of 6 at time 5. I got to the position of 20 at the 10th second, and then I got to the position of 25 at the 15th second. Maybe I traveled like this throughout the course of the 10 seconds. Okay, then I could say, all right, well, it's the same velocity the entire time, so maybe it's just the same as my average velocity. But are there other possible situations where I could have been located at the 20th meter mark at the 10th second? Yes. So what's the problem with looking at this table and trying to figure out what's going on exactly at this 10th second? I don't know what happens in between. Okay? But like I just showed you, so I'm going to say no. Even though I know where I am, this is not telling me what I did before and what after. I'm going to say no. But I could approximate it, right? I could take the average rate of change from maybe the 5th second to the 15th second and say, hey, if my dude moved consistently from the meter mark of 6 to the meter mark of 25, well then that will give me possibly the correct velocity. So I can just take the average rate of change of this, 25 minus 6, and divide it by 15 minus 5. And I get 19 over 10. Okay? There's an approximation. Is there another approximation I could do? So this is just saying my dude is moving consistently from the meter mark of 6 to the meter mark of 25. And as he crosses through the 10th second, even though he's probably not going to be located at 20, he's going to have to probably, you know, if I went consistently at, you know, 1.9 meters per second, I'm probably not going to end up at the meter mark of 20 because then I have 5 seconds to get to 25. It looks like I have to, you know, kind of go faster to get to 20 and then slow down if I'm moving consistently, right? So what could give me probably another approximation? Well, you can't really find the acceleration here. It's the same thing. I just have position and time. Maybe I can just find how he traveled from the 5th second to the 10th second. Maybe if he consistently traveled from the 5th second from position 6 to the 20th second, maybe that's what he did right at the 10th second at position 20. So travel straight from 6 consistently to 20, and then right there he's still consistently moving, and then maybe he slows down after that. Okay, so maybe I need to not do from 5 to 15 because that's not going to be great. Let's do from 5 to 10. That might be better. I don't know. It's just another approximation. And then maybe instead of 5 to 10, let's go 10 to 15. Because maybe if he's traveling at the average rates of 5 meters per second or 1 meter per second, that's going to be the exact velocity that he's traveling right at the 10th second. So maybe we need to do this one as well. I don't know, but what could give me a better approximation? You know? What do I need to have a better approximation? Yeah, maybe if I had where he was located at the 9th second and the 11th second, right? Wouldn't that kind of narrow the time at which we don't know what's going on? So maybe if I know he's at the 19th meter mark at the 9th second and then the 21st meter mark at the 11th second, then we know, okay, if he traveled consistently from there to there, I know he's going to be traveling 1 meter per second, right? That's better. Could we do even better, though? What would be better, Ms. Kruthi? Yeah, maybe if we knew the position of my dude at the 9.9999999 seconds and the position of my dude at the 10.0000001 second, well, that is even narrowing that time of what, like, I don't know, down till it's almost 0. What's that idea of getting infinitely close to a number? It's a limit. It's a limit. It's getting close to 10. It's approaching 10. It's going to be a number like 10 from the left. And then 10 from the right. And if you think about it, if you look at the position which will exist from 10 from the left, and you look at the position from 10 from the right, those two things are not right at 10. They're a little bit different. Hold on, I got to get the key to this. Okay? What is that going to look like? Well, my average velocity looks like a secant line. What is it going to look like if I take 2 points infinitely close together? and I connect them, it's going to turn into a line that will just touch my function at a point. This is what we call a tangent line. Okay, now for the key to the lesson. Secant lines, we already discussed, connect two distinct points. The slope of the secant line gives you the average rate of change of something. Your function, okay? Your tangent line is a line created by taking 2 points infinitely close together. They just touch it. And what was the average rate of change when those 2 points get infinitely close together? So if I take this point and make it infinitely close and then I extend it, whoops, we get a tangent line, and average rate of change becomes what? Yeah, an exact rate of change or an instantaneous rate of change. So a tangent line just touches, and the slope of the tangent line we say is an exact or an instantaneous rate of change. Break out your notebooks and write that down. That's important. All of a sudden, average rate of change turns into instantaneous rate of change. The remainder of the semester, we'll be talking about instantaneous rates of change of things or derivatives. Okay. Now, first we got to make sure we're comfortable writing equations given lines. We should all be familiar with the point slope form of equation. We should all be familiar that parallel lines have equal slopes. We should all be familiar with perpendicular lines having opposite reciprocal slopes. Great thing, and I won't do all these questions, you'll just review this while you do your homework, is that on calculus tests, if you're asked to write an equation of a line with this slope and this point, you can just leave your answer like that. And you're done. This is the equation of a line. Just because you get y by itself doesn't make it less of an equation or a better equation. Okay, so this would be the equation of this line. And you will have homework problems dealing with lines. Definitely go over those things. Remember, parallel lines equal slopes. Perpendicular lines or normal lines, opposite reciprocal slopes. Okay, but let's go back to the